Okay. Good morning, all. In last lecture, we have finished the discussion related to the what is the meaning of the phase diagram and different types of the phase diagrams. Now, in this lecture, we will discuss about the iron carbide equilibrium diagram. Before starting that iron carbon phase diagram, first you should understand what exactly will happen during the cooling process of the iron and during the heating cooling and heating process of the iron, then what are the different allotropic forms of the iron at different temperature conditions. And after understanding that, we will move to the actual iron carbon equilibrium diagram. Before starting that equilibrium diagram, we will see what is the meaning of allotropy or polymorphism, and what are the different allotropic forms which are present in the iron at different temperature conditions. Okay. Now on the screen, just you can see the definition of that allotropy. What is the meaning of the allotropy or polymorphism? Here you can clearly see that the existence of the metals in more than one crystalline form at different temperature and pressure conditions, that will be termed as the allotropy process. And that forms which are present at different temperature conditions, that forms will be termed as the allotropic forms of that particular metal. Okay, here you can see in the diagram here three allotropic forms are shown for the iron. Starting from the left corner, alpha iron, and below that BCC is written, that is the crystal structure of that alpha iron. Then gamma iron, below that crystal structure is written FCC. Then delta iron, again its crystal structure is written as BCC. I will explain in the same in the next slide. Okay, here you can clearly see that different allotropic forms for that particular ion along with the cooling curve, and their along with their crystal structures. I have taken one slide here, I will explain it. Okay, here on the left hand side you can see that that is the cooling curve for the pure iron. And on the right hand side diagram you can see that for the different temperature ranges, different micro whichever crystal structure they are having, that is indicated here. Now I will explain it parallelly. What will exactly happen in the cooling curve for that pure iron, and what will be the different crystal structures they will have during the temperature ranges. Now, above that, fifth, okay. Now, first of all, we will, as we are doing we are going to learn here the cooling curve. That we will consider, or we will take that pure iron in the liquid state. From the liquid state, first we will heat that pure iron up to the liquid state. Now we are doing the slow cooling, and against the temperature, we are going to plot the curve by taking temperature as a function of time. Then we will get the cooling curve, which is shown in this diagram. Now, above 1539 degrees Celsius, that pure iron will be in the liquid state. Just below that, from 1539 up to 1000 and approximately 1400 degrees Celsius, the temperature during this temperature range, that iron will be in the it will show the BCC crystal structure that you can see at the top diagram, top right corner, body centered cubic crystal structure. And this iron will be termed as delta iron, having body centered crystal structure, BCC crystal structure. Then from temperature within this range, from 1400 degrees Celsius up to 910 degrees Celsius, it will be having FCC crystal structure, and it will be having FCC crystal structure, and this iron form will be termed as gamma iron. Then below 910 degrees Celsius up to room temperature, this iron will be having BCC crystal structure, that is body centered cubic crystal structure. Okay. Now I will explain it again from room temperature up to the melting point. from room temperature up to 910 degrees Celsius. Here you can clearly see that pure iron will be having BCC crystal structure, that is body centered cubic crystal structure, and it will be termed as alpha iron. But you can see clearly here at 768 degrees Celsius, up to 768 degrees Celsius, this pure iron having BCC crystal structure will show magnetic properties, and it will lose its magnetic properties above 768 degrees Celsius, and it will get transformed to the non-magnetic or paramagnetic in nature. And the alpha iron which exists during this temperature range, that is 768 to 910 degrees Celsius, it will be non-magnetic in nature. And in the older days, in some books they have denoted this
Hello.
iron which exists. Yes. Is there any problem? Falke, if you are having any query, you can ask me. Shall I continue? Rajwal, Rajwal is there.
Yes, sir.
Can I continue?
Yes, sir.
Okay, I will continue. I will explain it again. Now, this left-hand side diagram, it will show the cooling curve for the pure iron, and during this cooling curve, at a different temperature ranges, whichever my crystal structure is there for that particular iron phase, that is shown in the right diagram. Now, I will explain it again. Whenever you are starting the heating process, from room temperature up to 910 degrees Celsius, that pure iron will show BCC crystal structure, that is body centered cubic crystal structure. And now the same iron, it will exist in the two forms. It will exist in the two forms. That will be, one will be magnetic in nature up to 768 degrees Celsius. Okay, from room temperature up to 768 degrees Celsius, the iron will show the magnetic properties, and it will lose its magnetic properties at 768 degrees Celsius. This temperature will be termed as Curie temperature for that particular uh, ion. Then it will become non-magnetic or paramagnetic in nature above 768 degrees Celsius. Now the alpha ion phase, uh, it will show same crystal structure, that is BCC, but just it will be paramagnetic in nature or non-magnetic in nature in this range, that is 768 to 910 degrees Celsius. This will be alpha iron having BCC crystal structure and non-magnetic in nature. It will be termed as beta iron. Okay, this is the beta iron phase. Then above 910 degrees Celsius, its crystal structure will get changed. It will get transformed to FCC crystal structure. Now, the pure iron having FCC crystal structure, that is face centered cubic crystal structure, and it will exist between the temperature range 910 degrees Celsius up to 1400 degrees Celsius, and this will be termed as gamma iron. Okay, this will be termed as gamma iron phase. Then again, when temperature reaches above this point 1004, above 1400 degrees Celsius, again phase change will occur, and this FCC crystal structure will get transformed to body centered cubic crystal structure, and this ion will be termed as a delta ion. And this delta ion phase will exist in the temperature range from 1400 degrees Celsius up to 1539 or 36 degrees Celsius. That is the melting point of the pure ion. Okay, from above 1400 degrees Celsius up to melting point of that ion, The iron will be in the body center cubic crystal structure, and this phase will be termed as delta ion. Okay, so these are the different allotropic forms: alpha ion, then beta ion, gamma ion, and delta ion. This beta ion will be also known as alpha ion with non-magnetic nature, or in some books they have written the term, used the term for this particular alpha ion, which is non-magnetic in nature. It will be denoted by beta ion. So, mm, kindly draw this diagram showing the cooling curve for the pure ion. This diagram is for cooling curve of the pure ion, and this diagram, it will show the different allotropic forms of the pure ion at different temperature ranges. Here you can see from almost from the minus 273 degrees Celsius up to 910. Only body center cubic crystal structure will be there. Okay, and this will be divided in two phases, that is alpha ion, which is magnetic in nature, up to 768 degrees Celsius, and from 768 to 910 degrees Celsius. Here alpha ion will be there, but it will be having non-magnetic nature. This will be termed as beta phase, that is beta ion. Okay, but crystal structure will be same from, you can say, from room temperature or from minus 273 degrees Celsius. Okay, if you conducted the different uh, if you conducted the deep cooling up to minus 273 degrees Celsius, that iron will be in BCC crystal structure only. Okay, from this temperature up to 910, only BCC structure will be there. This phase will be alpha ion. Then above 910 up to 1400 degrees Celsius, iron will be in face centered cubic crystal structure. It will be termed as gamma ion. And above 1400 degrees Celsius, again this FCC crystal structure will get changed to body centered cubic, that is BCC crystal structure, and this phase will be termed as delta ion. And above 1539 degrees Celsius temperature, that ion will get transformed to the liquid state. So these are the different allotropic forms: alpha ion having BCC crystal structure, then gamma ion having FCC crystal structure, delta ion having BCC crystal structure. Okay, the delta beta ion will not be considered as a allotropic form, as it is having same crystal structure, that is BCC crystal structure. Whenever there is change in the crystal structure according to the temperatures, means chemical composition will not change, only crystal structure will get changed, that we can consider as the allotropic form. Means iron will be having three allotropic forms only: alpha ion, gamma ion, and delta ion, depending on the temperature ranges. Please draw the diagram. That you can take the heading, that is allotropic forms of allotropy and cooling curve for pure iron. This diagram, first diagram, left hand diagram will indicate the cooling curve for pure iron, and right diagram will indicate the allotropic forms of the pure iron. Okay, please draw the diagram. I will wait for a few minutes. After completion, you can put that in the chat box that you have completed the drawing.
हॅलो काय झालं
Rohit, you are having any problem or any query?
Sir, your
No,
voice
sir.
is not audible.
No, no, just now I stopped for till that you will get completed that diagram.
Okay, sir.
Okay, okay. Now my voice is audible, na, clearly.
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, okay. Just draw the diagram, that is cooling curve for that pure iron and allotropic forms of pure iron. Just draw the diagrams. If you have if you have completed the drawing, please put that in the chat box so that I can move towards the next point. Sunil, roll number 62. Sunil, are you
Yes,
there?
sir.
Have you completed the drawing?
Drawings.
Okay, okay. Finish it, finish it.
Okay, sir.
Okay.
Now, sir.
Falke is there.
Hmm. Now, sir.
Please stop sharing your screen.
Huh.
Stop sharing your screen and unmute yourself. Whenever I will ask questions, then only you have to give reply. And don't start your video sharing also. Okay. Okay, I will move towards next slide. After the after understanding the different allotropic forms of the pure iron and the cooling curve of the pure iron. Okay, again, this is the same diagram. That is the cooling curve along with the different allotropic forms. Same diagram is here. Okay, this is the for left hand side diagram. It will means temperature and time. Here you can clearly see that this is the cooling curve for pure iron and different allotropic forms for the pure iron. Okay. Now, this is the next point, that is the volume changes of the pure iron. Whenever you are doing the heating or cooling process, first you should understand at which point the sudden volume change is occurring for the iron. Okay, because at the point where sudden volume change is there, if you are doing very fast heating or very fast cooling process, it will get cracked. Okay, whenever you are doing the very fast cooling or very fast heating process, if you can see in this diagram clearly here that there is sudden change in the volume, and it is plotted against the temperature. And here you can see that whenever that iron, whenever you are doing heating or cooling, whenever there is a phase change or change in the crystal structure is occurring at that particular point, here you can clearly see that at this point, means at 910 degrees Celsius, during heating process, this iron will transform from BCC, that is body centered cubic crystal structure, to face centered cubic crystal structure. At this particular temperature, when it is changing its crystal structure, there will be sudden there will be change in its volume. And similar way, whenever you are heating and at this particular point it changes its phase, from or crystal structure, you can say that that is from FCC to again BCC, that is gamma ion will get transformed to delta ion. And during this crystal structure change, again there will be change in the volume, means a large change will be there. At this particular point, if you are using very high heating rate or very high cooling rate, at this particular temperature point, the sudden cracking may occur. That's why during the heating process or during the cooling process, you have to do this process slowly. If you are doing at a very faster rate, then cracking will occur. Okay, for this is the for the pure iron only, volume changes of the pure iron at different temperature conditions. And why this volume changes occurring? Because at different temperature ranges, it will show the different crystal structure, or there will be change in the crystal structure of that ion. Due to that, volume change will be there, and due to that volume change, cracking may occur. Or to avoid that cracking, you have to select the cooling rate very properly. Okay, so this will be helpful in the selecting the cooling rate for whenever you are doing the heating, or suppose whenever you are doing the heating process, you have to select the heating rate, and whenever you are doing the cooling process, you have to select the cooling rate also. And this will be helpful for you to select that proper heating rate or proper cooling rate depending on the temperature. Here you can observe that temperature range, that is at 910 degrees Celsius, volume change is there, and at 1400 degrees Celsius, again volume change will be there. So to avoid the cracking, you have to select the proper heating and cooling rates. Okay, it will be very necessary to change the properties of that particular metal, or the, if suppose you are going to change the properties of that particular alloys, it will be helpful there. That will we are going to discuss in the next chapters. At that point of time, you will come to know the importance of selection of the cooling rate. Okay, so after this, please just write the heading and draw the diagram, that is volume changes of the pure iron. I will wait for 1 minute here. Please draw the diagram, and after completion of the drawing, put that in the chat box that you have completed the drawing. And if you are having any query, you can also put that query in the chat box. I will explain it. Okay. Now we will move towards the next slide. Okay, now this is the very important point, that is the iron carbide equilibrium diagram.
Hello, sir. Hello, sir.
Yes. Yes.
Sir, sir, screen is not visible.
Screen is not visible.
Yes.
Others, whether screen is visible or not. I think it is visible.
Sir, not.
So, click on the search image and pin the screen. You will be able to see the screen.
I think it's visible. Just pin on my name there. I have logged in from two devices. Click on any one devices from that. You will able to see that screen.
बस कर लो बस
Vinayak Gauri.
रे बाबा
Vinayak Gauri is there.
Yes, sir.
Ah, you have to pin on my name there. That list. On that list. Automatically you will able to get that presentation there.
No, no, sir.
All students are able to see it. From your side, you have done some mistake there. Pin on. I have logged from two devices. Pin simultaneously on both. Start. From one devices I am presenting. Whether it is called. Vinayak Gauri.
Yes, sir.
You are able to see that presentation now.
No, sir.
Just pin on my name from that list.
Yes.
Now it is visible.
No, sir.
Is it visible? No, two names will be there. Two device. I have logged in from two devices. Simultaneously click on both, one by one.
Sir, there are three
Yes, sir.
names in list.
But click on any one.
Sir, visible.
Visible, no?
Sir, visible. Sir.
Okay, okay. Now
Visible,
unmute
visible, sir.
yourself. Okay, okay. Thank you. Okay, I will continue now. So this is a very important point now. Iron carbide equilibrium diagram. Okay. Now in examination, compulsory 14 marks question will be there. Okay, on this point only. Now, questions will be like this. In one question, you have to draw the diagram. You have to draw this diagram indicating all the temperature points, all the composition points, and all the critical temperature lines. Okay. Yeah, it should be correct with in all respect, means whichever temperature points are there, whichever composition points are there, it should be correct in all aspects. Yeah, then you will get the, and you have to indicate all the phases. It will be for 6 to 7 marks, and one 6 to 7 marks question will be there on the reactions or transformations which are occurring in this diagram. That transformation reactions you have to explain. Three transformation reactions will occur in this diagram. Okay. Now before starting the actual diagram, okay, uh, first draw this diagram. I will wait for 5 minutes. Okay, 4 or 5 minutes. It will take some time. Please draw the diagram. Compulsory this question will be there. Draw the iron carbide equilibrium diagram showing all its constituents, or you can say that all the phases, then temperatures, and all the critical temperature lines. Okay. Now please start drawing. Please start drawing this diagram. On y-axis temperature is plotted, on x-axis composition is there. That is, here we have plotted the uh, weight percentage of the element carbon. Okay, now this diagram is for, it is the alloy of iron and carbon. Okay, starting from point 0, at this point pure iron will be there, and as we are moving from point 0 towards right hand side, percentage of carbon will goes on increasing due to addition of that carbon, and there will be the formation of different solid solutions. Okay, and depending on that, different phases will be there. First draw this diagram. After drawing this diagram, we will discuss about the different phases. Here you can clearly see the different phases, that is alpha. Okay, alpha phase is there, gamma phase is there, delta phase is there, and Fe3C. This is Fe3C is nothing but the iron carbide. Okay, please draw this diagram. Indicate all the temperature points, indicate all the phases, indicate all the critical temperature lines. Critical temperature lines means whichever lines are indicated by that A letter, that is A0, A1, A2, A3, like that. 4 or 5 lines are there. You have to draw that lines also, indicate all the temperature points also. Please draw the diagram, and after completing the diagram, we will discuss the different phases existing in it. And after studying the different phases, we will discuss whichever transformations occurring there, we will discuss that. Okay, I will wait. I'm waiting for from last 2 or 3 minutes. I will wait for again 3 to 4 minutes. Please complete it and put that in the chat box that you have completed the drawing. Okay, while you are drawing this diagram, I will explain the phases. Okay, simultaneously you have to draw also, and listen to my voice also. I will explain it here. In this iron carbon equilibrium, this diagram will be also known as iron carbon equilibrium diagram, or iron carbide equilibrium diagram also. Now here, main 4 phases are there, that is, I'll highlight here. First, this is the alpha, indicated by this alpha. This is the ferrite, it is known as ferrite. Okay, alpha. This alpha is ferrite. Then this Fe3C, it is iron carbide. Fe3C, iron carbide, is known as iron carbide, or simply you can term it as carbide also. And this is known as the cementite also. Okay, this alpha is nothing but the ferrite. This Fe3C is the cementite. Okay, this is first phase, then second, and third phase. This is the denoted by this gamma. This will be austenite phase, and this is the delta ferrite. Okay, these four phases are there. Okay, which exists in this iron carbide equilibrium diagram. Now, what exactly this phase is? Okay, what is this alpha ferrite or austenite or delta ferrite? What is this cementite? That I will explain one by one here. Now, please see here. This is alpha. Okay, this is the alpha ferrite. This alpha ferrite is a solid solution. Okay, this is a solid solution. Now, which kind of solid solution it is? It is interstitial solid solution of pure iron, that is Fe and carbon. Okay, carbon. This will be interstitial solid solution of your pure iron. You can say that iron and carbon at lower temperature ranges. Okay, from, you can say that from uh, room temperature, or from 0 degrees Celsius also you can consider it. From the room temperature up to the 727 degrees Celsius, or sometimes it will exist up to 910 degrees Celsius. Okay, this is interstitial solid solution of iron and carbon at lower temperature ranges. Okay, it will be termed as the alpha ferrite. Why the name is given as ferrite? Why here we are terming it as a ferrite? Because in the French language, that ferrum means the iron. From that French word ferrum, it is the word ferrite has been derived, and the name is given as alpha ferrite. And it is an interstitial solid solution of iron with the carbon at the lower temperature ranges. Okay, this will be the alpha ferrite. Now, what about its properties? As it is an interstitial solid solution, it is soft, malleable, and ductile in nature. Okay, this alpha ferrite is soft, malleable, and ductile in nature. But as the carbon percentage goes on increasing in that, it will gain some strength. That's why pure iron will be soft and malleable or ductile in nature, but you can see that its alloys, that is the steels, different kinds of the steels, or different plain carbon steel or different alloy steel, they will be having very higher strength, because due to the presence of this carbon element, it will gain the strength. So after this alpha ferrite, next phase, here again this alpha ferrite, it will exist from the room temperature up to 910 degrees Celsius. Okay, alpha will be there. Okay, now in this alpha ferrite, solubility of the carbon will be different for different temperature ranges. Here you can see here at this point, uh, at the room temperature or at the lower temperature, solubility of the carbon in this alpha ferrite phase is 0.008%, and it goes on increasing as temperature is increases, and it will be 0.025% at 727 degrees Celsius. This is solubility, or this much amount of carbon will get dissolved in this phase, or in this solid solution, that is the alpha ferrite. Now, this alpha ferrite will lose its magnetic properties at 768 degrees Celsius. It will lose its magnetic properties at this 768 degrees Celsius, and above this, it will become the non-magnetic in nature, and it will exist up to 910 degrees Celsius. And the phase, this alpha ferrite, which exists in this range 768 degrees Celsius to 910 degrees Celsius, it will be termed as beta ferrite, or simply alpha ferrite, which is non-magnetic in nature. Okay, so this is the alpha ferrite phase. It is nothing but an interstitial solid solution of iron and carbon at lower temperature ranges. Now, The next phase is this is the gamma ion. Now this gamma ion is also, this phase is named as the austenite because the scientist Austin first studied this phase. He identified this phase and he studied this phase in detail. That's why this gamma ion phase is also known as austenite. Now this will, what is this then gamma ion or austenite? Again, it is an interstitial solid solution of iron and carbon, but this is an interstitial solid solution which exists at higher temperature ranges, that is above this 910 degrees Celsius range up to 1400 degrees Celsius. Okay, this is the austenite phase. This is again interstitial solid solution of iron and carbon, but at higher temperature ranges. Again, this is a soft, malleable, and ductile phase, and it will be having. It is the interstitial. What is it? What is the difference between this alpha ferrite and this gamma ferrite, or it is termed as the austenite? What is the difference between this ferrite and this is the austenite? Then this is interstitial solid solution of carbon with iron having BC crystal structure, and this austenite is the interstitial solid solution of carbon with iron having FCC crystal structure. Okay, this is the difference between these two phases. Ferrite will be interstitial solid solution of carbon with iron having BCC crystal structure, and this will be interstitial solid solution of carbon with iron having FCC crystal structure. The both nature of this alpha, that is ferrite and austenite, will be soft, malleable, and ductile. And another difference is this austenite will be non-magnetic in nature, and this ferrite will be magnetic in nature up to 768 degrees Celsius. And on this both ferrite and austenite, you can do cold working process because these are soft, malleable, and ductile in nature. Then after this, the next phase is this delta ferrite. This delta ferrite exists in this region above 1400 degrees Celsius. Again, this is the interstitial solid solution of carbon with the delta ion phase. We have studied the different allotropic forms of ion: alpha ion, gamma ion, and delta ion. Okay, now this carbon will form interstitial solid solution with this respective ions. Here alpha iron and carbon, it will be termed as ferrite. Then gamma iron and carbon, that will be termed as austenite. Here delta iron and carbon, they will form interstitial solid solution and it will be termed as delta ferrite. And here you can say that this delta ion will be having BCC crystal structure there. Okay, in this way, these different interstitial solid solutions are there formed by carbon with the iron, and the iron will be having different allotropic forms of different crystal structures. Depending on these phases are formed ferrite, austenite, and delta ferrite. So these three phases are there. And the next important phase is this Fe3C. This is the cementite phase. Now this cementite is this is not a solid solution. Directly you can say that it is a compound or intermetallic compound formed by the carbon and iron. Here carbon will be present, that is approximately weight percentage of carbon is 6.67%. So this is the cementite. Now this cementite will be having orthorhombic crystal structure. Vinayak Gauri, please stop sharing your screen. Am I audible?
Yes, sir.
And then Vinayak Gauri, please stop sharing your screen.
No, sir.
You are sharing the screen. Whether my screen is visible to all?
No, sir.
No, sir.
Then why you are sharing screen in between, Vinayak Gauri? I have to start it again. Oh, whether I have done each one. Okay, I think some network issue is there. That's why I have logged out from that another device from where I am showing the presentation. Okay, I think time is about to finish. We will stop here only. I will repeat whichever part I have taught now regarding the phases. I will repeat that part again. Whether you are able to hear my voice clearly, Prajwal, reply me.
Yes, sir.
Okay, from any other student,
Yes, sir.
okay, from girl side.
Yes, sir, you are audible.
Okay. Up to which point you were able to see the screen? Up to that cementite phase.
Yes, sir.
Okay. I will repeat all explanation for all phases in next lecture also. Now time is about to finish, and some due to some network issue, I logged out from that another device. Okay, just 4 or 5 minutes are there. We will stop here and we will continue in the next lecture. Please try to practice drawing that iron carbide equilibrium diagram. Try to draw it 1 or 2 times and try to understand the temperatures, then phases, different critical temperature lines. Okay, is it clear?
Yes, sir.
Okay. Okay. Then we will stop here and we will continue this remaining part in the next lecture. Okay, thank you.